is also an important model, particularly in scenarios dominated by noise. This process is mathematically tractable and exhibits properties that make them ideal for applications in engineering, physics, and data science. This report will be divided into two parts, including Gaussian random variables and Gaussian processes. First, I will introduce the Gaussian random variables. A random variable W is defined to be a normalized Gaussian random variable if it has this density like this, where W has mean 0 and the variance 1. This is the same as the standard normal distribution. And we have learned in probabilities. If we consider the random variable z equal to sigma w, then the distribution function of z and w are related by fz sigma w equals to fww. The probability the densities are related by sigma fz sigma w equal to fww. The PDF is given by fz equal to this. And because the random variable z is a zero mean Gaussian random variable. Then the movement generating function MGF also we define it as the GZR of a zero mean Gaussian random variables can be calculated as follows. GZR equal to expected value of the exponential RZ, and we expand this and combine these two terms, we get this after simplify. So finally, we get exponential R squared sigma squared over 2. Next, we will introduce the Gaussian processes. First, the definition of the Gaussian processes is very easy. The Gaussian processes is a stochastic process such that for all positive integral t and all choices of a push t1 dot tk in capital T, the set of random variables xt1 dot xtk is a jointly Gaussian set of random variables. A stochastic process xt t in capital T, where t is integer real numbers, positive integer, or positive real numbers, is Weisner stationary if its back value of xt equals to its value of x0, and the covariance xt and t plus u equal to covariance z 0 to and u for all t u in capital T. Then I will introduce a special case in Gaussian process. The case is a discrete time Gaussian Markov process. Let alpha be a real number, the absolute value alpha is smaller than 1, and consider a stochastic process, which is defined in terms of previous examples of an IID Gaussian process. Wn by this xn plus 1 is equal to alpha xn plus wn for n in positive integer x0 equal to 0. And we can expansion it. So we get this xn equal to wn minus 1 plus alpha wn minus 2 plus alpha squared w minus 3 plus dot plus alpha n minus 1 w0. The covariance function of this is expected value xn plus k equal to sigma squared times 1 minus alpha 2n times alpha k 1 over 1 minus alpha squared. Since alpha absolute value of alpha smaller than 1, and the coefficient of alpha k is geometrically decreasing in k. Therefore, for large n, it makes a little difference whether the sum stops with the term alpha n minus 1 w0. or weather terms, we can write alpha n w minus 1 plus n plus 1 plus dot 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 as n to infinity. So limit n to infinity e equal to sigma square alpha k over 1 minus alpha squared. This suggests that this suggests that x n can be read as sigma j from 1 to infinity alpha j minus 1 w n minus g. Next, I will introduce the second special case. It's a Gaussian sign process. The sign function is defined as sin t equal to sin pi t over pi t. The Fourier transform of sin t is a square plus that is 1 for absolute value f is less or equal to 1 over 2 and 0 elsewhere. The most remarkable features of the sign function is that it and it translates over integer intervals from an orthonormal set, from an orthonormal set. It is. Here is the theorem of the Gaussian sign process. Let xt be a continuous square integrable real or complex function of t in real number, which is limited in frequency to minus b to b for any given b bigger than 0, then ft equal to sum n x n over 2b sum 2b t minus n. The theorem can be very easy to prove. That Vf is a square integrable function of frequency, where v in minus 1 over 2 to 1 over 2. Then the Fourier series of Vf over f in minus 1 over 2 to 1 over 2 is Vf is equal to sum n Vn ei 2 pi nf, where Vn can be written as this. Since sin t minus n is the Fourier transform of the Vf e minus I 2 pi nf, both frequencies limit to minus 1 over 2 to 1 over 2. So if ft is a square integrable continuous function whose Fourier transform is limited to minus 1 over 2 to 1 over 2, then xt can be written as this. Xn is the integral from the st sin t minus n dt. Since for any integral value of t, sin t minus n equal to sigma tn, so xn equal to xn then, so xn is equal to xn, then xt can be written as this. If we replace the sin t minus n to sin 2bt minus n, we can get the theorem proof. We can get this. Next, here is another definition. Now, suppose that Xn is a sequence of RAD Gaussian random variables and consider the following Gaussian sign process. Xt equal to integral sum from minus infinity to infinity xn sin 2bt minus n. This can be written as this. bt minus n, where n is in integer. Here's another theorem of the Gaussian sign process. The Gaussian sign process xt is the equation 7. This is a stationary Gaussian process with a covariance function sigma square sin 2bt. Here is the proof. the covariance function of the t and tau equal to expected value of the sigma n xn sin 2b t minus n times sigma k sk sin 2b tau minus k. We remove the square. So we can get this. Since its expected value xn times xk equal to 0 for k not equal to n, then this can be written as this. And the expected value of the xn square equal to sigma square. So we take out it, and write like this. And yt is equal to sin 2b t minus tau for any tau. The Fourier transform of yt is yf equal to square root 2b inverse times exponential minus I2 pi b tau f for f bigger than b or smaller than minus b or smaller than b, and 0 and elsewhere. Then by this theorem, we could get this. Since the covariance dependent only on t minus tau, the process is stationary, and the covariance in single variable form is the covariance ft equal to sigma square sin 2bt. Now, finally, I introduce the application of the Gaussian sum process. The application is a filter Gaussian sum process. A linear time invariant filter with an impulse response ht creates a linear transformation from input function xt to be an output function yt defined by yt equal to integral from the minus infinity to infinity x tau times ht minus tau d tau. We assume that ht has a Fourier transform that is 0 for the absolute value of f bigger than b, where b is the binomial of the input Gaussian sum process. We show that later that implies that the filter is not realizable. This is of no concern here, since our purpose is similarly to characterize a family of Gaussian processes as the filter output. Suppose that a stochastic process ft is the input to a linear time invariant filter. Let omega be an underlying simple space, and let omega be a simple point of omega. The corresponding simple function of the process st is then x is the st omega. The output of the LTI filter with an impulse response ht and input st omega is given by yt equal to this. If we express the sum process ft as in this equation, so we change the sum. So we change the xt tau to this. Yt can be written like this. We can change the integral and the sum position. We write as this. Sec 2b tau minus n ht minus tau d tau. Then the integral can be simplified. That far as it. So we integral can get the integral part is the 1 over 2b times ht minus n over 2b. So yt is the sum n xn over 2b ht minus n over 2b. If sigma n is square n over t minus 2b is final for each t, then yt t in R is a Gaussian process. Thank you.